Hi everyone, welcome to week 2. Now this week we're going to be extending our work with trigonometry into 3 dimensions. So I've just placed a few important rules here at the top of the page about just general principles for 3-dimensional problem solving. So first, draw a box around the object that you're dealing with and label all the vertices. So we can see one down here where some of the vertices have been labelled, but when we get to the problem solving ones, these unnamed corners, I'll be giving them names of my own just so we can keep working with other parts of the shape. Now look for things which are equal length, in particular heights. So we've got the height here at this side of this is 9. Because this is a rectangular prism, I could be quite justified in saying that length SP is also 9, and Q down to this unnamed vertex would also be 9. So that's interesting, and it could potentially be quite helpful. Now when we've decided what part of the diagram we are going to use, I recommend we redraw just a 2-dimensional version of that part. So perhaps just a triangle or something like that. Apply our normal trig rules. Now this final point, and this is the real key to these, you have to be able to get used to looking from above, from the front, and then from the side, and potentially even from the back and from the underneath too. And imagining this object in 3-dimensional space, and then drawing or just imagining part of it in 2-dimensional space, looking from one of those directions. All right, so now let's just get into this one and see how we go. Have a bit of a try. So we've got a box here which has had a corner removed, and we have to find the dimensions of length QR. Well, like I said, before I get too much further, I've already got PQRS. What if we go T, U, and V for these other vertices that we've got? So for part A, I'm interested in QR. I think if I was looking down from above, then QSR would be a lovely right triangle. So Q would be there. Coming across to S, this would be the right angle here in this corner if looking from above, and over there to point R. Now what do I know about this? I know that that angle marked in there is 45 degrees. And what else do I know? Well, here's one of these points about equal length. I know that it's 15 centimetres along the front edge here from point T to point P, and because this is a rectangular prism, QS would also be 15. So that's helpful. Now let's take a look there. That small angle theta would be 45 degrees because of the old adjacent angles rule, or the Z rule some people use. Now once we have that, then the length of QR shouldn't be a problem. Cosine of 45 degrees should equal 15 over QR. QR is then 15 over the cosine of 45 degrees. Now we should all remember that cosine 45 is 1 over root 2, so that would give me 15 root 2. Of course, we can use the calculator and have an approximate answer of 21.21 centimetres for QR. Now that makes sense to me because it's 15 along the front here from Q to S, and then it would be, as it's a 45, it would be another 15 along here. So that's handy to know. We've just figured out, being a 45-degree triangle, that looking down from above, this thing would have the shape of a square. So that's good to know. So might be handy later on. Part B. Calculate the value of x. So looking here at x, I'm looking from the side, looking from this way, and I'm going to be seeing a right triangle here with P, U, and R. So there's my right triangle. Just double check, P was there, U was at the far corner up to point R. Now what do we know? We know the height of this is 9, and Now, interestingly, just what we said a moment ago about SR is 15. So if SR is 15, then PU must also be 15 because it's a rectangular prism. So we can mark in 15 down here, which, and this is another point about this, often you'll need to rely on information from a previous step because it's all related, and angle X was down here in this corner. This one is now quite straightforward. Tan of X, and this is usually the way it goes. The hardest part of these is thinking about the diagram in 3 dimensions and pulling out the appropriate bits of information. So what did I say? Tan is that, so X is the inverse tan, that would be 3 on 5, and when I checked that I got 30.96 degrees. Part C was to calculate the angle of Y. So I'd have triangle PTQ. Here we go. PTQ. That was the right angle. Now the height is 9, like we said earlier. From over there, the base TP is 15. This is angle Y. It's going to be the same as we had a moment ago. So the tan of Y is 9 on 15. Y then is the inverse tan of 3 on 5, or the same, 30.96 degrees. So those two triangular faces here and here would be congruent. Now, final one, the angle that the triangular face PQR makes with the horizontal base. Now this is not as easy as it seems. It is not angle X and angle Y. That is not what we're talking about. The horizontal face, I'm going to embellish my diagram here. Imagine the midpoint of QR. Now because this is a square looking down from above, dealing with a square, that gives us a little bit of advantage, and a dotted line running down the surface of this face here to point P, that would be a right angle to QR because we've cut this QR line in half. But importantly, and this is what I really want to think about, I want to think about the vertical line running down the back of the diagram and then the base of the diagram, which as yet hasn't been shown. So there's the hidden detail in the diagram, and if we had a line running from that back corner, now where are we up to? We've got TUV, that back corner is going to be W, that's that back corner over there. If I have a line running from W through here to point P, and then I drop a vertical line down from my midpoint there, I haven't given that a name yet either, so I suppose that would be capital X, and that point of intersection would be capital Y. So I've got a right angle triangle in here. Now just zoom up a bit on that so I can help you see it. I'll highlight it in green. That's the line running down the middle of the oblique face. That's the line running across the base from point P directly to point Q, to point W, I'm sorry. Point Y would be directly below point X. And that gives me a triangle I can work with, and the angle I'm interested in is this angle in here, which I'll just label theta. Now what do we know? Well, if I was to redraw that thing from above, if I was to look straight down from above, I'd be looking at a square. So that would be Q, that would be V, that would be R, and that would be S. So that line there would represent the length YP, and that line there would be half of the diagonal. But we already know the diagonal. The diagonal was the answer to the first question. It was 15 root 2. So I'm going to now draw my diagram, the two-dimensional version, which is just that green triangle. There's the green triangle. That's point P. That's point Y, which is half right in the middle of the base. And that's point X up there, which is right in the middle of the top. My angle that I'm interested in finding, theta, is this angle here. I know the height of this thing would be 9 because our vertical line XY would match the edge there. And as we said, this horizontal base, that's half of the diagonal. So the diagonal was 15 root 2, and half of that is 2. Now it becomes child's play to calculate theta. The tan of theta would be 9 over 15 root 2 over 2. The inverse tan of whatever this comes to, let me just check, I did this before I started, it's 40.32 degrees. Now, that's that last bit at least was a little bit more challenging, so that's part D just over here. Don't be afraid to draw extra lines on your diagram. Definitely label every single point and the ones that you've added in, and look for those lines which are of equal length. Now, we were very lucky here in this one because we happen to have a square-shaped object. We could then use that half of the diagonal as the length we needed for the base of this triangle. Each of these is unique. Each of these questions, you have to take it as it comes, read the question carefully, and above all, don't give up. If you run into a dead end, go back to something where you knew it was right and try again. There's always going to be a way to solve this. Okay, that's enough for now. Good luck with solving your 3D trig problems.